Welcome to the ninth talk of Human Factors in Design. I'm Joseph Giacomin, and today we'll be discussing cognition, a very important topic, a topic which is the subject of hundreds of textbooks and thousands of studies. We don't have time to do full justice to the topic, but we'll try to introduce a few of the key terms and a few of the key concepts, such that you will be in a position to delve deeper into the many opportunities of designing based on cognitive principles. So today's topic, cognition. The first thing to note is that in the previous talk we mentioned that the human nervous system starts with a sensation arriving from our sensors, from our periphery. Perception was that amount of processing and that aspect of the processing that started to not just note something was happening, but compare bits of the view field or compare different frequencies in the sound to other ones in the surrounding to try to make sense of it. And we said in that previous talk that cognition was when we finally made sense of it and we're beginning to pass the information to the frontal cortex for our thought processes and some of the processes involved in decision making. Well, all of that, if we step back and look at the bigger picture of how humans behave, all of that feeds into what's referred to as the perception action cycle. Roger Sperry, a neurophysiologist, was one of the first individuals to put a specific name to it, the perception action cycle. And what the gentleman's referring to is the fact that human behavior tends to follow a certain pattern, and the human brain emerged to fulfill this pattern. And the pattern is that we do exploration of things in our world, samples, objects, experiences, other people. These experiences modify our mental models, which is our synaptic strengths in our cortex. This leads to some connectivities relating to schema or patterns. We see patterns in the environment, and we see schema or patterns in how we can respond to what we've learned with ourselves, with our body, with our thinking, with our actions and behavior. The schema tend to direct again our explorations and our seeing and our hearing and our experiencing the world, which leads to more exploration, encountering more objects, leading to more schema, and life is an endless perception action cycle. So today's discussion is very much about elements which are critical or at least quite important to this perception action cycle. Now, a few definitions which are helpful in a design context. The first definition, which most designers would have heard and many designers will use every day in their work, is that of affordance. Affordance is a concept first proposed in the 20th century by Gibson. The idea of affordance is that objects can have characteristics which announce or even facilitate their use. They invite a specific course of action, a specific interaction with them. And affordance can be, for example, in the case of what's illustrated on this slide, which is a simple rocker switch. An affordance could be referring in this case to the fact that something that looks like a seesaw, which has a rotary motion from one position to another and doesn't want to stop necessarily in between two positions, push in, push out, seems to be suggesting something is going on and off. The rotation seems to be a very natural thing to achieve with a finger or a hand. It appears that a rocker switch has an affordance. It's affording its user the ability to switch between two states, most likely an on and an off, as shown in this image. That's a type of affordance. Now, another term which comes from cognitive science, but which in design is very commonly used, is the term schema, which we already mentioned previously. A mental structure of preconceived ideas, a framework, a model, some pattern for representing information. A schema, quite often we talk about motor schema, which is the pattern of movement we do when we're playing a game or walking or doing some specific well-defined activity. A schema is a pattern, a model, it's a template that can be followed as actions by the person to solve a problem, to achieve a goal, to complete a task, to do something of some type. So schema are patterns we learn. We learn that if we want to read a book, we get to the bottom page and we turn the page over, flatten it, and start at the top of the new page. That's a simple form of schema. So schema are the patterns, quite often motor patterns we use to do things of the person. The affordance instead is the characteristic of the thing, of the artifact, inviting us to use the schema. So, next concept that's important to understand is mental models. First hypothesized in the 1940s. It's a psychological representation, could be real, could be theoretical, could be hypothetical, of some situation. It's used as a model to predict what might happen next. So if I know that every time I push my rocker switch in, which is labeled as the on position, the light on the ceiling will come on, that's a mental model of a simple cause-effect relationship. Once I've developed it, I use it for predictive purposes. I will not use the switch until it gets dark. Then I know if I go there and push it, something known to me and clearly expected will happen. So mental models are how we organize in our mind the world around us. Dogs bark, cats meow, airplanes should be up there and not down here, etc., etc. So mental models are patterns we learn and we use to do predictions and to guide our behavior. Now, mental models in many systems can be quite simple and straightforward, such as the one that's illustrated here. The mental model of a traditional classic desk lamp with only an on-off switch. Push the button on, I expect the light to come on. Push the button again, I expect the light to go off. I expect that the light has two states labeled on and off in the image, and that the action that I perform on the interface, the interaction that occurs, the simple press, should on each occasion move me from one state to the other, and if I keep pressing, it just keeps occurring in an infinite loop. That's the mental model. It's a causal relationship. If I do this, it should cause that. Now, mental models get complicated rather quickly, surprisingly quickly. For example, a type of lamp which was rather common in Europe until about maybe 40, 50 years ago, little bit less common these days, when things like electrical switches were still relatively expensive as a component, there were lots of lamps that had a multiple position switch. So I have one potentiometer or rheometer or some sort of electrical device, and I can switch between, I can open different circuits by switching it, turning it into different positions. With one switch, I can do several different settings. Cheap, inexpensive, practical way to make things when they were still relatively expensive, the components. So a rotary switch on a lamp of the type we used to have quite commonly in the past, you might have the lamp off, you grab the little handle, you turn it a quarter of a turn, and it might switch it on, but it switches the light bulb on to a 30-watt setting, so the light is not so bright. I turn maybe another quarter of a turn, and the light now miraculously goes to a stronger light, a 60-watt setting. One more quarter turn, I might go and get the 90-watt setting, and one further turn, and I'm back to the off position with no light at all. Now, functionally, from an electrical engineering point of view, a rotary switch like this is very simple. It's one of the simplest switches we can imagine, and it's very straightforward, not a big deal to make or to install. But as a mental model, it can be surprisingly confusing, because the direction of the turning and the quarter of the turn means that it's quite straightforward to get confused. If I turned it and I wasn't paying really close attention, particularly if there's no sort of indicator on the outside of the switch to tell me 1, 2, 3 which setting it's in, if it's the really simple type there used to be in the past that you turn it and you have to feel the turn, what would happen here is quite often you turn it on, you'd look at the light and you'd think, oh dear, is that the 30 watt or the 60 watt? I'm not 100% sure. The difference isn't that huge. Let me try turning again, see where I am. Oh, it's still coming up higher. One more turn, I'm off. Oh, I guess it was the 30 watt. Let me go back to the 30 watt. It's very simple with this continuous rotation, which instead of going from a state back to off, it goes from state to state to state. It's very simple to get confused. If you're not able to judge the intensity of the light really accurately, a person can get confused. And with these lamps, I recall very distinctly in the past having encountered lamps like this, and I'd sit there, and quite often, on more than one occasion, I would turn it on, be totally unconvinced of which of the states, 30, 60, or 90 watt I was in, and keep turning around till I'm back to off, and then count it carefully. Click, click, click. Okay, definitely I'm in the maximum now, even though I'm not a good judge of light. I listen to the clicks. I got it. I'll leave it there for a while I read my book. So something as simple as this, as a mental model, which is very essential, can nonetheless already, at this level of complexity, create some human confusion. And as I've said, these traditional rotary lamps with different settings were a constant source of confusion for people. And later, as electronics evolved, lots of systems came down the line. Lots of new products and services were produced, which were much more complicated than something like a rotary switch with a few settings. And these new innovations quite often led to great confusions with the mental model. One of the classic examples that a person finds over and over again in ergonomic and human factors textbooks is the remote control for a standard television. You would think it's not particularly complex things, because the basic function of a television is choose a channel, choose a volume for the sound, and possibly have some option somewhere for adjusting the image. But when we started to introduce not just the television, but also the VCR, and also maybe add to the controller the stereo, the home stereo system or something else, very rapidly these remote controls began to confuse people quite systematically. For example, here we have an example of a fairly standard TV remote, which permits you also to control the VCR or the video recorder, which these days, of course, is not so much used. You have the television, the recorder, the stereo, and it looks like there's a cable TV channel selector as well. Seems that there's 4 things you can control, and then there's channel volume, or put in the number of the channel directly for the things you do on the thing that's being controlled. Doesn't seem so complicated to do this. Instead, these fairly standard controllers in the 1980s and 1990s in particular created a lot of problems for their users. For example, one of the classic problems that's in many books about human factors is the mute button. On many of these controllers, there was a mute button, as can be seen here on the image, the fairly large button below the arrows. The mute button, of course, you push it to make whatever you're controlling go quiet when you get a phone call or when someone knocks at the door and so forth. Now, the way the controller is laid out, it seems fairly natural. Most people seem to have been doing this back in the 80s and 90s. People were assuming that since it's such a simple thing to mute, it would be applicable or it would work with any of those 4 devices which are being controlled. Instead, in many cases, for the remote control, actually the mute was a function that was only technically implemented for the television. It wasn't going to work, it had no connection, it had no way of doing a mute for the VCR or the cable channel. So what we had here was a mental model where a person thought, I've got 4 things to select at the top, and I've got a set of buttons at the bottom which are going to be equally applicable to any of the 4. That seems like completely separate. There's this bit and that bit, and what's down here probably going to work for all the ones up there. That seems like a very natural thing. In the 1980s, it was obvious most people were assuming that. But then technically, the transmission standards and the IEEE standards, in many cases, there wasn't a simple way to do it. So we had a conflict or a mistake in the mental model where a person was assuming what's shown here in the middle, and what was actually technically the electrical circuit that was implemented based on the standards and techniques of the time was what is shown on the left of this image. So mental models can very rapidly diverge from the physical reality unless the designer is incredibly careful to consider this issue, talk to people, find out which models they're deploying, and try to make close match between the functions of the artifact and the mental model of the functions which the human being would have. Mental models are incredibly important in design. They help people to structure their understanding of things, help people to think about things. It provides the logical basis for interacting and for interaction design with the thing. Mental models, because they very quickly can diverge from the reality, it's important that a designer ensure that the same mental models being assumed at every point of the system, at every stage of design. So if we have several different menus on the app, if we have several different functions on the controller, we should be assuming a mental model which people seem to be using, and we should design every menu and every button and every option starting from the assumption that's what the person's going to be thinking. So where do we put the button? What do we call it? How do we avoid them going to the wrong one if that's the mental model that probably most people are adopting? Another aspect of mental models is they are constructed. You're not born with a mental model of a remote control or a lamp in your mind. Mother Nature had no need for remote control or mental models millions or hundreds of thousands of years ago. So much of this, if not most of it, is learned from experience, and thus, if it's constructed sociologically from experience, it does mean there will be some effects of cultural stereotypes on the system. So in different parts of the world, with people of different ages, possibly there may be occasionally effects related to the gender of the individual. There will be some cultural stereotypes which will affect the expectations which are part of the mental model. So a designer has to ask the question, if I make this button red, does it mean the same thing in the United Kingdom as it does in Russia? Does it mean the same thing in the United Kingdom as it does in China? What might be the cultural stereotypes which creep in to the structure of the mental model and thus need to be considered and accommodated? And also, it's very important, as listed at the bottom, time delays. to system responses have to absolutely be minimal. You have to reduce the time delays. It's not just a matter of frustration. It isn't just that when you're using your cell phone and you push a button and the little thing starts to circle and it seems to be taking forever for the system to complete the action that you requested. It's not just a matter that that is a little bit confusing and somewhat frustrating. The real problem here is if the time delay is too long, you lose track of cause and effect. If I push the keyboard twice and the response to the first keystroke was so slow that when a response finally occurred, I wasn't sure anymore whether the thing I'm seeing is the response to the first keystroke or the second, we've got a complete breakdown of the mental model. So one of the big design parameters, which most designers probably don't give enough attention and enough consideration to, not even those who come from a human factors background, is the question of time, the temporal dynamics. If too much time passes between an action and a response, between choice and a function being executed, we have a potential for breakdown of the mental model due to the loss of causality. This is a huge problem, particularly with electronic systems such as computers, cell phones, navigators in the car, and so forth. There's no point in telling me I'm supposed to exit at junction 3 if I just passed already junction 3. And yet these things are happening all the time, because quite often there are time delays in calculations and transmissions. Now, another issue related roughly within the field of cognition is the question of the metaphor. Designers work a lot with metaphors. Human factors and ergonomics experts quite often give some consideration to the possible metaphors which lie behind certain actions people took or certain expectations they might have in relation to some product, system, or service. So what's a metaphor? An expression that describes a person or object in terms of some other person or object, usually one that's a bit simpler and easier to understand. For example, what's listed at the bottom. The mind is an ocean, the city is a jungle. We're talking about the human mind, which is incredibly complex, and comparing it for some particular purpose in some particular conversation to an ocean, to emphasize the vastity of the data involved. The city, in some conversation, someone is trying to say a city is a dangerous place and there's lots going on and you don't know what you're going to bump into when you turn the corner, and the person uses the metaphor, the city is a jungle. So one thing, usually a very complicated one, that we're trying to focus some attention on in terms of some specific characteristics, is being referred or put in reference to some other one which is known and understood and usually is substantially simpler to understand for some reason, and thus we can focus attention on what we want to focus attention about the more complicated one. So metaphors are about understanding one thing in terms of another. Usually a metaphor is taking something that's very familiar and simple and using it to help explain something maybe less familiar or more complicated. Most human thought processes are metaphorical. People focus on language or mathematics or other things humans do to talk about communication. But language and mathematics and other tools are not really the essence of communication. The essence of communication is the pattern, the ensemble, the group of ideas and characteristics and actions and situations and colors and smells that come together as a group or a block, as a package. Human thinking is about connecting together one thing to the other by finding which characteristics or which historical events or which colors or whatever they have in common. So human thought processing is mostly metaphorical. We use a word to represent a whole group of things. We take an action, we choose a thing to represent a whole group of possibilities. It's metaphorical in nature. And metaphors are usually not arbitrary. Usually they're based on physical and cultural experience. There's certain things that exist in our world. There's certain things that happen in our world. If I take something and I let it go, it drops down due to gravity. These often are embedded or built in as part of the metaphors we use every day in our talking, in our acting, in our choosing, in our working. One type of metaphor that's been described in the 1980s in quite great detail by Lakoff and his colleagues in several books was the category that's referred to as orientational metaphors. The examples on this slide are textual examples, they're words. But the ideas here are ideas that designers have to keep in mind if they're going to avoid violating the mental models and the thinking processes of the people that the artifacts are being made for. What are these orientational metaphors? Orientation, direction, up, down, left, right. Happy is up, sad is down. In the English language, you can say, I'm in high spirits, up. I'm feeling down, down. I fell, downwards, into depression. Conscious is up, unconscious is down. Get up, wake up. He fell asleep. He dropped to sleep. More is up, less is down. Good is up. Things are looking up. It's been downhill ever since. We have hit an all-time low. Rational is up. Emotional is down. So all languages have orientational metaphors in their structures because all human thought processing tends to have orientational metaphors embedded in it. And the ones we're seeing here for the English language are quite typical of most, probably all, languages. Certain good things are up, certain human nice things are up, other things we like less tend to be assigned a downward direction. As a designer, are you going to make the switch that turns on the fan and speeds up the fan? Are you going to make the switch go up, or are you going to make it go down? Well, if you're making it go down when you want the fan to speed up, we've got a problem. We're violating a mental model because the metaphors are even deeper than the model itself. They're part of the structure of thinking that produced the model. Other types of metaphors, which perhaps most people haven't stopped to think about. We don't usually stop in the middle of the street and give thought to metaphors, but metaphors are everywhere around us. They're in everything we say and everything we do. Here's three, which I think everyone will recognize quite quickly from the examples. Entity and substance metaphors. We need to combat inflation. It will take a lot of patience to finish this course. He broke down. Okay? Here we're talking about treating characteristics, treating parameters, or treating values as if it was a thing. We need to combat inflation. Inflation is when prices go up. It's just a statistic. It's not a monster. It's not an enemy. It's not a person trying to break into our house. What does it mean to combat and fight something that's a number? But we treat things in this way because it makes it simple to try to understand what we're getting on about. Fighting inflation means we'll have to take some actions to defend ourselves from inflation. Even though it's just a number, the number comes from somewhere. We'll have to take some practical actions to avoid it. Container metaphors. I was in the forest. There is a lot of land in Kansas. He is in love. He's inside of love? In it? Is it a container or a room. So you can see again, to convey some parameters, to convey some characteristics and some information, we take something such as a room and we use it as a metaphor for something more complicated and less easy to describe and more mysterious, which is love. And personification, a very popular one that we read in the papers and the magazines every single day of the week. Life cheated him. Cancer finally caught up with him. She is sailing out of harbor tomorrow. Life cheated him. Life is a person or a thing. She's sailing out of harbor tomorrow. The ship is a lady. Okay, so you can see where we're going here. Making some fuzzy value, some fuzzy idea into a person makes it helpful to understand that there may be a reason for the behavior we're seeing, there may be a cause-effect relationship, and it might bring some parameters with us. The same with the containers, the same with the entity metaphor. So metaphors are bundles or groups of ideas that we take one and apply it to the other to try to help someone to grasp some aspect of the other one. Now, other things that designers have to be worried about and concerned about, if we understand things like the perception action cycle, affordances and schema, we understand there may be metaphors occurring in the person's thinking, and that might be part of the mental model that they're adopting. All of that's great. We can use that to design things. So let's take a mental model that's very much about this metaphor and let's make it sure it's consistent all through our design. But once we're getting on with the design and we're starting to have some complexity and detail and fine detailing of things, we do have to begin asking some questions more related to the actual interaction itself, the details of the interaction. And one of the first very, very important issues, one of the dominant issues, is the question of workload. Workload defined as shown here in this slide, the amount of work or the working time involved to do something, to achieve some goal or achieve some task, the amount of work performed or the amount a person is capable of doing in some period of time, etc., etc. These concepts of workload, meaning the machine needs me to do lots of things and I'm getting tired and I don't know if my body and my brain can keep up and make all the right decisions and complete all the tasks and all the actions that are required. These issues, like so many of the other things we've discussed in previous talks, got a big acceleration in the 1940s, again for the same reason. The machines that were used at the time, think of the fighter jet, for example, think how fast a jet aircraft flies compared to a piston engine airplane, compared maybe to the Wright brothers airplane. And you can imagine very quickly at those speeds, with those kinds of complexities of aerodynamics, we're starting to have requirements of a pilot which are starting to go and stretch the person beyond their perception and thinking and reacting abilities. So workload, can I do it? Or does it need more than what I can achieve, what I can provide? That starts to come into play at that point. So mental workload, various definitions, they have a lot in common, but there are some subtle variations. The mental effort that the human operator devotes to controlling or supervising something, the cost of performing a task. So in one case we talk about the mental effort, the other is the cost in general, including physical, muscular cost. Mental workload refers to the portion of the operator information processing capacity or resources that is actually required for the task. So there's always something in the definition about the machine needs me to do a lot of things, and physically and mentally I may have some constraints, and I may be struggling to be fast enough or accurate enough to keep up. So mental workload, when is it that this gets to be a big problem? And it's many systems today that we all use every day put us into difficult situations with mental workload. It's a very common problem. You don't have to be the pilot of a fighter jet to struggle sometimes to use a system accurately and correctly. The kinds of situations or scenarios which create high mental workload and put some stress on the operator tend to have at least these 4 characteristics. Stimulus driven and not self-paced. It's one thing to be following a radar screen and simply turning it on to check things out of curiosity. It's another thing to be asked to do a 12-hour shift watching a radar screen looking for incoming aircraft or missiles from a potential enemy, and knowing that I probably only have 10 to 15 seconds to react and call emergency to bring up the air defense systems. And if I'm slower than that in my reaction, we may be too late to defend ourselves from the assault. It's one thing to pace, choose, decide yourself on a Sunday morning what to read, what to do, and which task to complete. It's a totally different thing to be in a stressful situation, asked to monitor something continuously, possibly without intervals, and knowing that there's potentially very little time to respond. So stimulus driven rather than self-paced, the fact that I can't just walk away and get a cup of coffee is a source of great stress and very high mental workload. Large fluctuations in demand. If I'm doing a job on the London Underground which requires me to look very carefully at traffic or footfall conditions before I take certain decisions to do certain things, it's one thing to be doing this at 11 o'clock at night on a Wednesday night when there's very little people in the system. It's another thing to have to be chasing emergencies and making decisions continuously during the 4:30 to 7:30 rush hour at Hammersmith Station. So large fluctuations in demand, the fact that there may be periods of time with very little request upon us, and then other periods of times in which suddenly, dramatically, we have to leap into action and we have very little time to decide things, so forth. These variations, the fact that it's not relatively constant and consistent, but the fact that at any instant something can occur and suddenly the demand shoots up, this is usually a source of high workload. Multiple simultaneous tasks. It's one thing to monitor one channel on the heart rate monitor. It's another thing to be asked by the doctor to monitor 4 or 5 different channels simultaneously and to warn the doctor if there's an anomaly or an aberration or something unusual occurring on any of the 4 or 5. So having to do multiple tasks at the same time and split your attention between the different ones of different nature is a high workload condition. And then finally, high stress, high consequence. It's one thing to play a poker game and bet a couple of pounds on some hand. It's another thing to be a radar operator looking for incoming missiles at the air defense station and knowing that if you make a mistake and call a false alarm and say there is an attack when there isn't an attack, you could start a nuclear war. So the stress of the consequences, which isn't strictly related to the interface itself and the machine you're dealing with, is part of the psychological loading which makes the mental workload much higher. And the situation with mental workload, in a very simplified manner, just to get the point across in general terms, looks a little bit like what's in this diagram. The dotted or dashed line at the top that's right across on the horizontal, that's the attentional capacity of a given human being. The line at about 45 degrees, the straight line going upwards, is representing a task which over time, as you can see, as it goes from left to right in the diagram, it's getting bigger and bigger and bigger. So something's building up, requiring more attention. And the red line that goes across straight and then drops, the red line is the performance. How many times the person pushes the right button, how many times the person makes the right decision or says the right thing, how many times does the person react in the most appropriate, expected manner to the situation. As you can see, as long as the task is well below what is the physiological limit of a person to process information based on all the things we've been talking about in previous talks, no problem, performance is good. As soon as we start to cross these two lines, one on the other, we now have a problem and performance drops. And you'd be surprised, particularly in military applications, how rapidly a battlefield scenario can quickly cross that line and put a person in a situation of having to monitor so many events in the situation and make so many decisions in a small amount of time that the performance drops and mistakes occur. So mental workload is a very important thing. Now there's numerous methods that designers can just borrow from the internet, from various research sources, and use them to evaluate the workload of the thing they're designing. So if you're designing a computer software or an interface or an app or some new system you're putting on the expensive new car and so forth, you can quickly knock together your prototype, get the main functions implemented to get a minimum viable prototype, and then you can test it with people. And there's lots of methods for doing tests. Now, I could show at least a half dozen different methods which have slightly different specializations and flavors to them. I'll limit my discussion to one because I think it gives the idea, and you can quickly search on the internet for many others. But one of the more popular ones that most people are familiar with is the NASA Task Load Index, developed over a course of perhaps 20 years of work. You can imagine NASA between aircraft and the moon missions and spacecraft, how quickly the interfaces of these devices, these environments became complex and complicated. The NASA Task Load Index provides a very simple set of self-rated, subjective evaluations given by the operator, the test participant, who tells you what their opinion is using a Likert scale, either 5 or 7 points is the main scale, and gives you responses to these questions. How much was the mental demand, low or high? How much was the physical demand? Driving a car, for example, push the pedals, turn the wheels, quite a bit of physical demand, aircraft the same, and piloting aircraft. What is the temporal demand? Do you think you had enough time to do them? Or do you feel that everything was so rushed you were constantly making mistakes and really stressed out? Performance, do you think you were able, with the controls laid out the way they were and everything designed the way it was in our current prototype, do you think you were able to do the job well or not? What about the effort? Did you feel this really wore you down and made you tired or not? And frustration. If all the top questions have been answered, there's still the question of what did you expect from this interface? We're designing an interaction here between you and some system, you and some product or service. You must have had some expectations and some targets in your mind about how much you were willing to do to get the job done. Well, did that get violated? Did you get frustrated as a consequence? Give us some feedback there. So NASA TLX touches upon a whole series of things, and there's other scales which have more questions, more details, touch upon a few other issues and so forth. But this gives a flavor for the kinds of things that can be done to evaluate design concepts and design hypotheses a person has in terms of the specific issue of workload. That's not the same as customer satisfaction. There's lots of ways to measure different things, but when you're measuring mental workload, this is one approach. which is very popular. And because it's popular, there's hundreds and hundreds of studies which have published numbers measured in this way. So you can easily say, I'm designing this. Here's what I got from 10 people doing some tests. Let me see how my numbers compare to flying an airplane that the guy published his study a few years ago. Let me see how it compares to using a home stereo. Let me see how it compares to some apps on the cell phone. You can usually dig out a few other studies of other people who've used the same method, and that puts into context a little bit the numbers that you're seeing coming through on your design. Now, in terms of design classics, one obvious choice which came to mind as soon as I was preparing these materials was the famous Nokia 1100 series. Some of the younger people probably won't have experienced this device, but at the time when it first came out, this device was rather different and quite interesting and in many ways quite satisfying compared to some of the other products offered by other companies at the time. The Nokia 1100 series phone was a phone where there was a very obvious, determined, systematic intent to simplify the interface down to the minimum number of menu options, the minimum number of button clicks you needed to confirm any menu options, and the minimum number of control buttons themselves. There's a button for your home page and your phone book. There's some numbers for typing in selections or typing in phone numbers, but there's not a whole lot more than that. So this phone was designed by the people over at Nokia with great attention to principles of human factors and ergonomics coming from psychophysics, memory, cognition, with a lot of focus on things like workload and certain other targets of interaction design. And the Nokia 1100 at the time was a very satisfying device, so much so that even today there's a bit of nostalgia and there's some heritage branding going on, and there's still some of these units using the same keyboard on sale today, because despite the fact they don't do everything that the modern cell phone would do, the amount of capabilities they have, for that amount of capabilities, they're amazingly simple, straightforward, and pleasing to use. So there's a certain pleasure in using something that's made so much simplification so clearly. So the Nokia 1100 is definitely designed based strongly on workload, metaphors, psychophysics, and memory, all the things we've been talking about recently, and it's a great example of a design icon which does a very good job in terms of its cognitive characteristics. Another design icon, again from a cognitive point of view, is the TomTom Navigator, something that nowadays is integrated into most people's cell phones as a map, either offered by Google or Apple or someone else. The TomTom Navigator, when it first came out in the 1990s, the cell phones didn't have the maps at the time. The TomTom Navigator was a very significant product because, like the Nokia phone, the TomTom Navigator was a tour de force, or an excellent example of cognitive design and sensory perception design. The TomTom Navigator was putting on the screen only the minimum number of informations a driver actually wants or can use while they're driving. From a technical point of view, so many items of information could have been selected for display on the screen at any one time. But the people who were developing this tool realized and recognized also from consumer testing that when you're driving and you're busy and there's a lot going on, potentially you might even be in heavy traffic and have to be keeping an eye out at the distances of the other vehicles and the behaviors of the other drivers, your cognitive workload is very, very high. And your cognitive overhead, the amount of space you have left for the mission planning or the route following, which is what this is assisting with, might be surprisingly small. So if we put lots and lots of items of information, multiple items of information which need monitoring on the screen, we're further increasing the workload, possibly with little benefit. So the screens were visually attractive, they were visually highly simplified, the most relevant items of information were projected in very simple formats with very large fonts and very large icons. Colors were synchronized to standard expectations and stereotypes. The whole layout is trying very hard to give you enough to do the job and nothing more, because your cognitive workload is already incredibly high in the driving task. So the TomTom Navigator, and it did win several design awards because it was obvious to people that it was simple and clean and well designed and very functional in its job. It won several design awards, and it's a great example of designing things aesthetically pleasing, lots of clever things going on, but all of it is paying attention and respecting the cognitive considerations or the cognitive constraints which the driver is undergoing while they're doing that task. So a very good example of also cognitive design. So thank you very much for your time and your attention. I hope there were some useful items of information for you today in this discussion, and I look forward to talking to you again next week. So thank you very much.